You know, telescopes, they're like these amazing time machines, right? They let us peer back to the very dawn of time. But have you ever stopped to think about how they actually work? Like, what's the science behind it? Well, the story is pretty fascinating, and it starts somewhere you might not expect, somewhere way, way closer than a giant observatory. So let's just dive right in.
Okay, but before we get into the nitty-gritty, I've got a quick question for you. When I say telescope, what pops into your head? I'm guessing it's something huge, right? Like a massive observatory perched on a mountaintop, or maybe the famous Hubble Space Telescope orbiting Earth. But what if I told you the most common telescope on this planet is something else entirely? What do you think it is? Go on, take a guess.
Ready for it? The answer is your own eyes. Yep, you heard that right. Every single one of us has a pair of incredibly sophisticated biological telescopes built right into our heads. And it turns out, if you want to understand how we build these massive machines that can see to the edge of the universe, you first have to understand the one you use every single day. All right, so let's start there. To really get how we build these giant cosmic eyes, we've got to look at the physics that makes our natural telescopes tick. It really all boils down to one fundamental principle: refraction. And don't worry, it sounds technical, but it's actually super simple. Refraction is just the bending of light when it passes from one thing into another, like from the air into the water in a glass. Your eye's lens is an absolute master at this. It bends the light coming in just so to create a perfectly sharp, focused image on your retina at the back of your eye. That's it. That's how you see. Okay, so our eyes are pretty amazing, right? But they're not perfect. They have their limits. And that's where human ingenuity comes in. For centuries, we've basically been building technological upgrades for our eyes. Bigger, more powerful, giant eyes, really, all designed to smash through our biological limits and see what's way out there, beyond what we could ever hope to see on our own. So, when you're trying to build a better eye, there are two things that matter more than anything else. First up is the light collecting area. The best way to think about this is like leaving a bucket out in the rain. The wider the bucket's opening, the more rainwater you're going to collect, right? It's the exact same for a telescope. The bigger the lens or mirror, the more light it can gather, which makes super faint, far-off objects look brighter. The second thing is angular resolution. Now, this is all about detail. Think of it like the difference between an old fuzzy TV and a brand new 4K screen. The better your angular resolution, the sharper the image. You can see two stars that are incredibly close together as two distinct points of light instead of just one big blurry blob. And this really gets to the heart of it. When it comes to telescopes, size absolutely matters. Let's make this real for a second. Imagine you've got a 2-meter telescope, and then you've got a monster 10-meter one. Now, the 10-meter one is 5 times wider, right? So does that mean it collects 5 times more light? What do you think?
Nope, not even close. It's 25 times more powerful. And that's because the power doesn't just go up with the width, it goes up with the square of the width. It's all about the area. So just by making a telescope 5 times wider, you get this massive 25-fold leap in its power to see faint stuff. And that is why astronomers are in a constant race to build bigger and bigger and bigger telescopes.
So, how do we build these things? Well, there are really two main designs. The old school way is the refracting telescope. It uses a big lens to bend light, kind of like your eye does. The more modern design is the reflecting telescope, which uses a giant curved mirror to bounce the light to a focus. Now, refractors are cool, but making a gigantic, perfect piece of glass for a lens is incredibly difficult and heavy. Mirrors, you can build them huge, and that's why pretty much every single major professional telescope you see today is a reflector. It's just the better design for going big. Okay, so you've built a giant telescope. Problem solved, right? Wrong. There's another huge obstacle we have to deal with, and it's all around us. It's our own atmosphere. Seriously, trying to look at the stars from the surface of the Earth, it's like trying to get a clear view of a coin sitting at the bottom of a swimming pool while people are splashing around. Everything gets blurry and distorted.
I mean, for an astronomer, the atmosphere is a total nightmare. That turbulence is what makes stars twinkle, which sounds romantic, but for science, it just means a blurry image. Then you've got light pollution from our cities, which creates this ugly orange glow that completely washes out faint galaxies. Oh, and did I mention clouds? And the fact that the atmosphere literally blocks most kinds of light from even getting to us in the first place? Yeah, it's a real pain.
But astronomers are clever. To fight back against that atmospheric blur, they came up with this brilliant piece of tech called adaptive optics. This is seriously cool. It uses a special mirror that's actually flexible, and a supercomputer makes it change its shape hundreds of times every second. It analyzes the twinkle from a star in real time and bends the mirror to perfectly cancel it out. It literally takes a shimmering, blurry mess and turns it into a tack-sharp point of light. It's just an incredible piece of engineering. But even with a trick as amazing as adaptive optics, there's an even better way to solve the problem. The ultimate solution? Don't even deal with the atmosphere. Just get above it. Put the telescope in space. And here's where things get really interesting, because getting a clearer view is only part of the reason to go to space. The other, even bigger reason is that it lets us see the universe in all these colors of light that our eyes can't perceive and that our atmosphere completely blocks. It unlocks a totally invisible universe. Think of our atmosphere as a wall with just a couple of small windows in it. One of those windows lets in the visible light that we can see with our eyes. And there's another, bigger window that lets in radio waves. But that's pretty much it. All the other kinds of light, like high-energy X-rays, gamma rays, and most infrared, get slammed shut. They're totally blocked. So if you want to see what the universe looks like in X-rays, for example, you have no choice. You have to go to space. And seeing this invisible light takes some seriously clever engineering. Take X-rays. They're so high energy, they would just punch right through a normal telescope mirror like it wasn't even there. So how do you focus them? Well, X-ray telescopes use these wild-looking sets of nested, barrel-shaped mirrors. The X-rays come into this super shallow angle and just kind of skip off the surfaces, like a stone skipping across a lake, until they're gently guided to a focal point. It's brilliant. Radio telescopes are a bit more familiar. They look a lot like those giant satellite dishes you see. The reason they have to be so big is because radio waves are really, really long. So you need a huge collecting area, that giant dish, to gather and focus them effectively. And because radio waves are one of the things that do get through our atmospheric window, we can build these enormous arrays right here on Earth. So let's recap. We figured out how to build bigger and better eyes. We figured out how to put them in space to get above the atmosphere. So what's next? What's the next great leap? Well, it's not about building just one even bigger telescope. It's about linking lots of them together to create a single virtual telescope that's as big as an entire planet. The mind-bending technique that pulls this off is called interferometry. In a nutshell, it lets you combine the power of two or more telescopes so that they work together. And when you do that, you get the same level of incredible detail, that's our angular resolution again, as if you had one single gigantic telescope as big as the distance between them. It sounds like magic, but here's the basic idea in 3 steps. First, you get a bunch of telescopes, sometimes on different continents, and you point them all at the exact same object, at the exact same time. Step 2, all the signals they collect are sent to a central supercomputer, which does some incredibly complex math to combine them, lining them up perfectly. And step 3, out comes an image with the same ridiculously sharp detail as if you had a telescope the size of the entire Earth. It's just staggering. And that's the real takeaway here. Interferometry isn't about making things brighter, it's about making them sharper. It's all about that angular resolution. This isn't just theory, either. This is the exact technique that the Event Horizon Telescope used to take that now famous first ever picture of a black hole's shadow. A single telescope could never have done that. It was only possible by creating a virtual telescope the size of our planet. So think about that journey for a second. We went from the simple physics of light bending in our own eyes, all the way to creating planet-sized virtual telescopes. We are constantly pushing, constantly inventing new ways to see farther and clearer. We've built these incredible artificial eyes that can literally see back to the dawn of time. And the best part is, the journey is nowhere near over. Which leaves us with the most exciting question of all. What will they show us next?